Hi there, so welcome back. We're finally releasing this new tutorial. I'm very excited about. We're going to finally be diving into the NVIDIA Modulus library, but the whole thing. You know, in the past I have showed you how to install it, how to run it, but in this tutorial I'm going to show you how to actually dive into the modules of the library in a Jupyter Notebook, because this is the most comfortable way to actually see the objects in the notebook. On every cell we can see the contents and we can break it down and we can see how the different components of the library work. For example, we can see how to declare the domain, the boundary constraints, the interior constraints of a partial differential equations problems, of a PDE problem. So yeah, here I'm mentioning the interior constraints. We're going to understand how to set up the solver, the configuration, all of that. How to, at some point, where is how do we instantiate the architecture? Somewhere we instantiate architecture. Yeah, here. Yeah, also how to instantiate the architecture. I'm going to do it slightly different from the documentation. We're going to actually do it in a more explicit manner because I want to show you how it works behind the scenes a little bit, the architecture of the neural net. And let's see, then we run the solver, and lastly, something I'm very excited about, I'm going to show you how to understand the output files, how to load the model from a file, an output file, meaning that you can give this to someone else, and if they know how to load the model as well, they're going to be able to use that to insert inputs and take outputs, which is the whole point of having a model. So here we play a little bit with PyTorch tensors and inputs, and yeah, finally we visualize the results and we replicate basically what we can see in the guides. So we're going to be following a guide with a few changes that I made to make it work on a Jupyter Notebook. We're going to be following an introductory guide in the official documentation, the lead-driven cavity stuff, the example. And so, for example, they show you how to visualize the results with what they call an inferencer. We're not going to be adding the inferencer, like the point-wise inferencer, because that's for visualizing the data on tensor boards. And I'm going to talk about TensorBoard and NVIDIA Modulus on a future tutorial. I'm also going to show you how to run that in a Colab Jupyter Notebook. But in this tutorial, I don't want to use TensorBoard, because what I want to do is to let you understand what you can do with the output files. Let you understand how you can get plots out of inserting inputs of the domain and getting the outputs, and how you can visualize that with matplotlib. So basically that's what they do behind the scenes. They don't show you how matplotlib does this, I guess, but if you do it with matplotlib, you get almost the exact same plot. As you can see, it even has the same default colors, and it's the exact same thing, evidently. But if you know how to manipulate the inputs and outputs, you can do cooler stuff and represent the visualizations, present the visualizations in a cooler manner. And we're going to get this plot, this vector field. You can't get a vector field from the TensorBoard add-on that they have, but if you know how to manipulate the inputs and outputs, you can do anything. You can deploy this on a cloud function, who knows what you can do, and do cool stuff, right? Whatever you want. So that's what I want you to understand. I'm like this because I have a software engineering background, so I want to be able to manipulate the objects. I just don't want the answers prepared for me if I can't manipulate the output at all. I think if you're creative enough, you can do cool stuff with output. So you gotta learn how to actually manipulate that, and that's what we're going to learn. Requirements. Well, I really don't know much yet about neural networks. I'm learning. So if you're like me, this tutorial is for you if you want to get into that. I'm getting into that in the space of scientific computing. So maybe you are a scientist, an engineer who knows about partial differential equations, who understands that, and who knows a little bit about simulations with numerical methods. This tutorial is ideal for you because part of the beauty of NVIDIA Modulus is that if you understand the problem domain, then really this tutorial is going to show you how you can get the inputs and outputs as long as you can define the constraints, the loss function, right? The boundary conditions and the interior conditions. If you know how to define the problem, you can use the library. In reality, the neural network part, you can just follow along and instantiate the model of the neural network, and you are going to train it, and you're going to get the inputs and outputs that you care about. You don't need to be an expert or know perhaps anything about neural networks. Now, if you learn about that, I suppose that's going to be helpful because you're going to get a sense of how it may be working behind the scenes, and you may also be able to use different configurations. So for example, in this tutorial, we're going to use something they call a fully connected architecture, which, to be honest, I don't understand fully. I understand that it's fully connected neural network, like every layer is fully connected to the next layer. So I understand that, but my understanding doesn't go as far as to, for example, I'm going to also show you the different architectures that they offer. Like they have a file, like if you go to the GitHub repository of Modulus Symbolic, the NVIDIA Modulus Symbolic library, you can find the arc.py file, and here are all the configurations. Unknown configuration, distributed, AF and O configuration, deep zero configuration, Fourier configuration, fully connected configuration, which is the one we're going to be using. It has this layer size and a lot of the activation function. If you learn about neural networks, you're going to learn about activation functions as well. But here we're just following with this one that is pretty fine for us. Convoluted fully connected configuration. And there are so many here. And I suppose if you learn about neural networks, you can test different configurations and you can test different parameters and you can exploit the library. However, you may not know a lot about this, then you just use this predefined configuration and that's fine. You define the boundary conditions, you define the interior constraints, and you define the partial differential equation, and boom, you get the results of your simulation, just like you do with any other software or numerical method that is more traditional and has nothing to do with neural networks. Learn to define the problem, reap the benefits of the library. And if that's as far as you know, you're okay. You're going to really enjoy this tutorial. Okay? So let's go. I have this little guide here with me. We're going to pretend that you guys are going to pretend that it doesn't exist. I can cheat because I can see it on another monitor that I have on my left. But I want to code it along. So the first thing we're going to do is install NVIDIA Modulus, right? On the Google Colab notebook. By the way, please change your runtime type. You may want to use the T4 GPU. So you can go to runtime and change runtime type, and you change that up before continuing. Okay? So very easy. So pip install NVIDIA Modulus sim. Don't forget the exclamation mark, by the way. So we're installing NVIDIA Modulus as well. It doesn't hurt, I guess. But the one we care about for this tutorial is NVIDIA Modulus sim. You may want to visit the installation guide, NVIDIA Modulus getting started. I'm going to be linking this in the description. Here they describe the different ways to install the stuff. We care about pip install because we're using the Colab notebook. In the past, I have a video. I'm going to be attaching the video of how to deploy NVIDIA Modulus to Google Cloud with Docker, but we don't care about that right now. We're using Google Colab. This channel is all about understanding the different ways we can deploy scientific computing. Okay, so we run this. It takes a little while. It's a heavy library. Very powerful. So we wait a bit for the installation to come through. Okay, I was getting impatient. It was taking a while. It takes like 3 minutes, I think, to install the whole thing. So after it installs, you gotta restart the session. It's going to prompt you. It's going to tell you restart the session. So you click there. That's okay. So you restart the session. And if you're not sure it worked, you can always click again and restart the session. That's okay. It installs a lot of stuff. But now we can keep going, okay? So now we have installed the NVIDIA Modulus library on Google Colab, okay? So the next step is to import the required libraries. Import required libraries. And there are a few that have nothing to do with NVIDIA Modulus. So, for example, import this one. This is just required. Import these ones. We're going to be needing this one as well. Import PyTorch, please. Important for visualization part of the tutorial. You don't need to have it imported with NVIDIA Modulus itself, because I think it imports it behind the scenes. It relies on it. But in this tutorial, we're going to use it to instantiate inputs and outputs of PyTorch called tensors, and in the visualization phase of the tutorial. Okay. Because of that, we're going to also import matplotlib. Again, this is for the visualization part of the tutorial. Now, you don't need SymPy to work with NVIDIA Modulus symbolic, because it's symbolic. All it means is that it allows you to manipulate and instantiate equations, like partial differential equations, like the Navier Stokes equations in this tutorial. These make use of SymPy, of course. So these are the non-related to NVIDIA Modulus libraries that we need nonetheless. Okay, so we import that up. Now I'm going to show you here, we're cheating again for a brief moment. For educational purposes, I'm not going to import the whole thing, you know? In the guide that you should check out as well, here in the documentation. So they import everything from the get-go. Now this is a lot of stuff to import, and I figure we're going to import it by parts. You can import it all if you want. You are going to have access to this notebook as well. But I'm going to avoid that because I want to explain every part of the library, right? So for example, the first thing we need, like, so if you want, you can copy and paste this in your notebook, I guess. Again, you're going to have access to it. But in our case, we're going to start talking about the Navier Stokes PDEs, okay? So, right, so from Modulus, symbolic, equations, PDEs, this is a really good breakdown of the library. They have done a great job. We can find a number of famous partial differential equations already defined for us. If you are working on a problem that it's not here, then obviously you need to define it yourself with SymPy. But in this case, the Navier Stokes is famous enough, so we have it here. So we import Navier Stokes, right? Okay. And I can show you this object, for example, like import Navier Stokes. Yeah, so the way this works is like ns Navier Stokes. We imported the class, but we need to instantiate the class, in fact. New, which is a famous parameter of the Navier Stokes equations. Raw, which is another parameter. And dimension 2, we're working in 2 dimensions. It's a steady state problem, so time is going to be false. And you can read about the Navier-Stokes equation here. Right, nu is the symbol. Rho is the density. So because the density is 1, you can see it here, but yeah, I should have well, I will assume you are familiar with the Navier-Stokes equations, but it doesn't work. Navier-Stokes equations. Okay, yeah, I like this image. So the Navier-Stokes equations, so they have the density somewhere in here. Where's the density? There you go. The density must... Where's the density? Yeah, I think it's here. Yeah, this is the density, right? It's a parameter. But this term is not relevant because we're not dealing with time in the problem we're working on. The density we can't really, I mean, it's 1 in the problem we're working on. And yeah, then we have the viscosity coefficient, which is new. But these are details that you may be familiar with, and I'm not going to be talking about so thoroughly. Anyway, the point is this viscosity coefficient new, the density is going to be 1, the dimension is going to be 2, and it's a steady state problem. If you have more questions about this setup, you can always check the example we're following on the documentation. They talk about the lead-driven cavity flow problem. Okay, you can get familiar with that. I also have a tutorial on that one that is with more traditional methods. I'm going to be linking that as well. Okay, so basically we instantiate the Navier-Stokes object. And what does it have? I mean, we just print it. Well, we can't say anything there, but we can place a dot here and see what it has in it, right? Dimensions, well, obviously that's 2. Equations, that's more interesting. Name, whatever. Well, equations is the most interesting one. So we can see that it has continuity equation, the momentum x equation, and the momentum y equation. And we can use this way of printing it, which sort of gives you that's not preprint. Well, that's interesting. That's interesting because when I tried pre-reprint, it printed it like this. Isn't that funny? Yeah, that one is not too important. Let's see. Interesting. Well, if you know how to get the pre-reprints like this, which may be useful for latex, let me know. Okay, anyway, but there are other ways to actually visualize it in a cool way here in the Jupyter Notebook, like if you do here continuity. Oh, yeah, make sure you use brackets, not parentheses here. You're going to be able to see our instantiation of the continuity equation in this case. U is what we don't know. V also we don't know. We're going to simulate that function is the solution to our partial differential equation problem. 1 was the parameter that we use. Okay, and as similarly equations momentum x. Yep, it's very explicitly showing it, but that's okay. When it comes to understanding NVIDIA Modulus, you need to understand the library, but also the problem itself, which has nothing to do with the library. So if you want to investigate more about Navier-Stokes and the lead-driven cavity flow classic example, you can do that as well on the side. But this is the problem we're working with. The Navier-Stokes steady state problem, 2 dimensions, with this set of parameters. And you can read more about it in the documentation of NVIDIA Modulus introductory examples. Okay, so that's what we have here. I want to show you though, and this is very important, I want to show you that you can check out the repository itself of NVIDIA Modulus. Let's see. Yeah. So in the NVIDIA Modulus, I recommend you download that. In fact, I have it here downloaded. And check out the Navier-Stokes.py file, which is in the PDEs folder, as we know. And so, for example, this is example actually where I learned this, how to leverage this problem. So they also instantiate the Navier-Stokes thing here, but if we click on VS Code here, like I think the best way to explore the repo is actually downloading it and using a text editor like VS Code. And for example, you are checking out the example, lead-driven cavity 2D, for example, and you click on go to definition of any class you don't know what it's doing, and you want to understand, okay, what is this doing? Like, I don't even know what it's doing behind the scenes, so check it out. And you're going to learn about the class, and they explain here, actually, for example, like the compressible Navier-Stokes equation, and they even give you here, I think it's the same. Oh, that's interesting. Yeah, it's an awesome site. Yeah, we're learning together as we go along. Yeah, so this link gives you here an awesome introductory text about the Navier-Stokes equations by NASA. That's cool. Would be cool to work there. And so it gives you the parameters, new, and the kinematic viscosity coefficient, rho, the density of the fluid, dimensions, time, mixed form, whatever, and the samples here, preprint. For some reason, this is how preprint should be looking. So it's funny it didn't look that way for us. That's very strange. It should have. Yeah, but it's not that important. If you want the latex form of this, yeah, this is how you would get it. And it instantiates the stuff. You may need to practice a little bit with SymPy to get this, but you can, if you know the concepts in math, I think you can make sense of this as well. Yep. So you can always dive into this with more detail, but this is how you explore it, right? And I think it's worthwhile to sort of like dive into the whole library through VS Code, because, for example, we can also go to instantiate architecture. See, this is a util, model configuration, or architecture here, go to definition, then we end up in arc.py, and we can find cool stuff. Or in VS Code, we can more easily say, okay, I want to, yeah, we end up in, like, for example, like, we do fully connected, right? What is that here? Like, fully connected. And we figure that fully connected is, yeah, it's here, fully connected architecture. Fully connected architecture. Models, arc.py. Look at that. I just learned that there are different files called org.py. There are two, in fact, apparently. Org.py. It's Command P on Mac, arc.py. There are two. There is a Modulus, symbolic models, arc.py, architecture.py, and there's a Modulus, sim Hydra. Hydra is for configuration and machine learning. Yeah, that's basically what it is. It's a way to, it's a library for doing configurations in machine learning very easily. You can check that out. But yeah, that's interesting. So there's an arc.py in about Hydra, and there's one for models, right? The one for Hydra has, for example, these data classes are very useful. The one for models, it seems it's more like abstract, I think. Yeah. The one we're going to be looking closely at is this one. The one that has the data classes. Because we're going to instantiate the architecture that way, right? The original problem has instantiate.arc and uses a configuration file. And you can read more about that in the documentation. But I am a software engineer and I like to use the objects because then I feel like I get a sense of what I'm actually doing. The configuration file is saving this step for you, but I like to see the parameters and the classes because that's the language that I speak as a software engineer. Okay, so yeah, there we go. So we keep going. Okay, yeah. Okay, so next step, the neural network, finally. Okay, so let's do the neural network. Let's go to our cheating notebook for a moment again. So the docs recommend defining the neural network architecture with a configuration file, which I just talked about. Let's check that out. So instantiate architecture and use this configuration file, which supposedly you would place, let's say, like if you're doing this, it should be placed in the configuration folder and should have a name called config. For example, here, configuration folder, config.yaml file, and it has these configurations. And we use the fully connected architecture, as I mentioned. So that's what they're doing here. They do it that way. But I don't want to do it that way. But we will do it with code. This is because we want to understand what actually happens behind the scenes a little better, and that is why I also recommend you to check out the arc.py file, which I'll just show you in the NVIDIA Modulus repository, where the data classes are defined, and this is here, as I just showed you in VS Code, but you can also go to the link here, whatever. So yeah, in that file, the arc.py on the Hydra folder, in the Hydra folder, we're going to see this, as I showed you here, fully connected configuration with these parameters. The way they do it in the introductory example is with this, right? But we're skipping this, but you can see it here. So, but we care about this way of doing it, okay? And there's another link here where they actually teach you how to do it this way. I think, yeah, so they teach you how to do it explicitly, you know, the explicit initialization, if you wanted to, which is what we're going to do, because that's a totally different link. That wasn't in the introductory example, but it was the way I liked to implement it explicitly, right? Okay, so let's do it. So we need, again, from Modulus sim models fully connected. Look at that, yeah, you know, it makes sense, right? It's very well broken down. Symbolic models. Well, in this case, it's more about the neural network. It should have been called neural network models or something like that, but it means it's the symbolic library of NVIDIA Modulus. Import fully connected architecture from Modulus sim models activation import activation. Oh no, wait, it comes from models because we're using this class, I think. Fully connected, no, we're using the one arc.py from models, right? Fully connected architecture. No, fully connected. Where is that class? Fully connected architecture. I really want to see where that class is. Oh, so it's here. Interesting. Models, and it has its own thing. Interesting. Yeah, so the fully connected configuration is just a configuration, but in reality, it doesn't instantiate the fully connected architecture. You need to use the class fully connected architecture in this file, fully connected.py, to actually instantiate the fully connected architecture. Okay, got it. Interesting. Yeah, so, and then we have activation functions, a class for that, and yeah, we import that. Very interesting. FlowNet, fully let's import this, right? FlowNet, I imported so that I have the auto completion. Fully connected architecture. Yeah, if you hover over it, you can see like a little example they have here. And we're going to actually test this example later, just because I want to show you something in the output and visualization part of the tutorial. Okay, but for now it's fully connected architecture. Input keys, key X, key Y. Again, this is the input of our problem, the domain, right? The domain is the input, or input coordinate X and Y. Then we have the output keys, what we don't know, U, the function we don't know in the partial differential equation problem. For a given X and Y, actually there must be one U, right? That's another way to think about it. It's actually, we're thinking about points here, right? X and Y point, of course, an input corresponds to UVP output at a given point in the domain. U is the horizontal component of the velocity, V is the vertical component of the velocity, and P is the pressure. And this is the science and engineering knowledge. And that's as far as you need to know, the inputs and outputs, and the definition of the problem, and the constraints, which we're going to cover later. Neural networks knowledge, you don't need to know. It's better if you know it, and you're probably going to learn it, I'm sure. I believe in you. But for now, you can just literally copy this. 500 layers in our neural networks, and in our layers, I actually don't know what that is. I need to check. We're going to have another tutorial focusing on these things, I guess. But skip connections, false, activation function. I do understand what is an activation function. I have a visualization of a neural network that uses in this channel, the ReLU function, the rectified linear unit function. In this case, it's the sigmoid, something like that function, I think. The silo function. It's an activation function, silo function. Sigmoid linear units, I think those were the classic ones before ReLU, if I'm not mistaken. Correct me if I'm wrong. So we're using that activation function, adaptive activations. I don't know what that bit is, but part of this is to demonstrate you that it's okay if you don't know everything about neural networks. You can still use NVIDIA Modulus and weight norm true. Yep, I don't know this bit, and that's okay. I don't know everything about these parameters. I'm learning neural networks as much as you. But the beauty about the NVIDIA Modulus library is that you can use inputs and outputs. You can define that. You can define the constraint. You can define the math, and you can get the simulations. You just need to understand how to leverage the library, and that's what this tutorial is about. Okay. Assuming I don't have any typos. Key is not defined. Oh yeah. So we need another bit here. Where is key defined? I'm looking at. Yeah, I got it. NVIDIA. Yeah. Okay. Cool. We also need from Modulus sim key import key. Okay, cool. I made a typo in our layer. What's going on here? In our layers, yeah. This is the only issue with doing things explicitly. You gotta get it completely right. In our layers. So now we have this object. Beautiful. Awesome. Now the next step is to make sure we have the whole set of nodes in our problem. So we make the nodes out of the partial differential equation model we have, and the nodes of the neural network model we are defining. The way I'm understanding this right now is that the flow net is sort of like the model we want to train, and we add these nodes because these nodes are going to take the constraints. So the partial differential equation, that's the part of the model we already know, and that's the part of the model that takes the constraints very explicitly. But the whole process is about training a network that resembles what we don't know. That is an approximation about what we don't know. That's why when we take inputs, we're in the output and visualization part, we're only going to need the flow net, because the flow net represents UVMP, the functions UVMP. They take x and y, and they give you u at a given point. They give you p at a given point. They give you v at a given point. But during the training phase, we need constraints. And the model that takes the constraints is the mathematical model that is a partial differential equation. That takes the boundary constraints, the interior constraints, and as I understand it, that's why we put this together right now for the training phase. But when we're evaluating the outputs, we'll need the flow net, because the flow net is what takes x and y and gives you u, p, and p. Okay? You're going to see that later. Okay, that's my understanding. Feel free to add more in the comments. Make node. Okay? And we get nodes. The first three nodes correspond to each of our partial differential equations. The continuity equation, the momentum x equation, the momentum y equation node, and lastly, the flow net, which is UVMP, taking x and y. Okay? That's the approximation. Right. Okay, cool. That's how I'm understanding it. Now, next step, the geometry. The geometry means the domain. We can learn about it in the introductory example, creating the geometry. This is our geometry. It's just a rectangle, so we're going to get that. They also have another file here I wanted to show you, I think. I don't have it here. There was a way to visualize the geometry. Yeah, they talk about how to visualize the geometry on a Jupyter Notebook. Here. Our geometry is too simple, so we're not going to visualize it, but you can learn about that, how to visualize that a little bit here. They also show you how to visualize a little bit the neural network definition, I think, if I'm not mistaken. Yeah, here's the fully connected architecture, and they teach you how to visualize that a little bit. I don't think it's that useful. It's like a lot of nonsense if you don't know about neural networks, I guess, so you can forget about that. I don't want to confuse you or confuse myself for what it's worth. So we're going to just keep going. As I already explained the understanding of the setup. And now the geometry. Now it's just a rectangle, so 0.1 0.1 height. Same for the width. It's a square, really, right? Symbol X and Y. Rec is a rectangle. All of these are classes of SymPy, I think, if I'm not mistaken. So yeah. But you know, it's divided by 2, right? Because we take it from the center. So we're taking it from the center, right? So it's 0.05 to the right, 0.05 to the left, 0.05 to the bottom, 0.05 to the top. Total is 0.1 height, 0.1 width. And that's our geometry. That's what we're defining. That's all it is. Oh, but we need the rectangle class. Oh, look at that. Interesting. Oh, I said it was from the SymPy library, but apparently it is from the Modulus library. Primitives, 2 dimensions. Look, that's interesting. Primitives, 2 dimensions. Oh, they have primitives for 1 dimension, primitives for 2 dimensions, and for 3 dimensions. So line, wow, that's obvious. Channel 2D, rectangle, circle, ellipse, polygon. That's cool. I wonder what's in 3 dimensions. Primitives, plane, channel, 3 dimensions, box, of course, vectorized boxes. What else is here? Sphere, torus, that one is good. Cone, triangular prism, tetrahedron. I wonder what you do if you have really complex geometry, like an actual machine geometry or something, like a beam or something in civil engineering, or a dam in hydroelectrics. That would be cool to learn how to define that. I wonder if you learn how to set up these classes, maybe you can do more complex stuff. Anyway, so but it all comes from SymPy, I think. Yeah, it comes from SymPy. Interesting. Look at that. Very powerful libraries. So we get the geometry here. Okay, that's just an object. That's funny. Okay, cool. Now the meat of science and engineering. The meat of science and engineering simulations. Constraints. That's what we're doing now, okay? So first we need the domain, right? Domain, okay? So the domain is LDC domain equals to domain. Again, oh, domain is not defined. Okay, that's cool. So again, another class we need from NVIDIA Modulus. The domain class. Again, all I'm doing is following the example. Perhaps doing a few things differently, like the instantiation of the flownet, but this comes from this example, so you can check that out too, which is this introductory example, in case you didn't get that already, which I've mentioned a lot of times. Okay, so we get the domain. Now the boundary constraints. All partial differential equation problems and simulations talk about boundary constraints. So we need the top wall and the no slip condition. So what's that about? Very quickly, the top wall has the constraints that the horizontal component of the velocity u has a velocity of 1, right? That's the magnitude of the velocity in that component. The direction is horizontal, so that's why we're talking about the horizontal component. The vertical component, I think, is 0. Yeah, there. It's supposed to be 0 there. And it has a no-slip condition. What does a no-slip condition mean? It means that the fluid doesn't slip in the boundaries. It means that it's static at the boundaries. So that's why the no-slip condition is going to have zero velocity for both components in all the other boundaries. The left boundary, the right boundary, and the bottom boundary. The velocity of the fluid there is zero. Now, is that realistic in real life? You can do your research about that. I think it's an idealization. You can assume that for some reason the fluid at the boundaries gets like sort of, it doesn't move there, like the particles of the fluid that are at the boundary, they're like velocity zero there. They don't slip. Imagine the friction is a lot there, I don't know. Yeah, so we need to define these constraints. I'm convinced the lead-driven cavity flow problem is a very boring problem. I hope we're going to talk about more exciting simulations in the future. Let me know about those. I want to do rocket simulations. That's cool. So top wall, point-wise boundary constraint. We need another class for that one, a few classes, in fact. So let's import those. So from modulus sim domain constraint import, we can import a point-wise boundary constraint, a point-wise interior constraint, and that's what we need: the boundary constraint and the point-wise interior constraint. Oh, sorry, yeah, so we import that. I think they also have a class called point-wise constraint, apparently. I suppose it's the parent class for the other two. We don't need that one. We need the point-wise interior constraint and the point-wise boundary constraint. Right now we're dealing with boundary constraints. So I'll put this here. So boundary constraint. Okay, so the top wall. What did we say about the top wall, guys? We said, so we need to give the nodes. That's just a requirement. We need to give the geometry. That's not that's just another requirement. The important part here is the out variables, right? The constraints. We said that the horizontal component of the velocity is going to be 1 and the vertical component of the velocity is going to be 0. I just explained that with the figure. Use that, you can see it again if you want. So the way they do it in the example is they have another parameter, the batch size. You can read about the batch size. It's forget about it. It's not that important. You can read the definition. Batch. I'm going to show you where you can see the definition. Top wall. That's defined in the configuration file. Right. It's 1000. Now I haven't defined a configuration file here, as you can see. So we're going to do that later. In fact, at some point we do need it, but for now we can get away with doing it explicitly. So batch size of 1000. I think the batch size, we talk about the batch size here. The constraints batch size here in the introductory sample, of course. The constraint batch size argument specifies the number of points to sample on each boundary. Okay, cool. So we have a boundary and we're going to sample a number of points there. 1000. That's a lot. Fair enough. The criteria argument is optional with no criteria. Oh, that's another parameter anyway. So we're here. So the batch size 1000. How many points to sample in the boundary? Lambda weighting. Well, there's a lambda weighting parameter. We're going to wait for that one. So there's a criteria. Obviously, like, where is this supposed to happen? Well, we have a condition, right? Where y happens to be of half the height. That's y equals 0.05. That's the top wall, right? Okay, so that's how they do it. And there you go. Now they have something they call the lambda weighting. It's a little bit of a funny thing, you know. I'm going to show you. So they have this function. So we're going to copy it. It's the lambda weighting. So the point of the lambda weighting is nothing but to make sure that the value of the velocity u is 0 at the corners, because having 1 at the corner and then 0 for the horizontal component, like if you have 1 at the corner and right below the corner you have 0 again for the horizontal component of the velocity, that creates a sharp discontinuity, which is a problem in simulations and numerical methods. So this kind of weighting just makes sure that as you approach the boundary, things get to be 0 there, to avoid sharp discontinuities. That's the concept. They have a link here. They talk about spatial weighting of losses, I think. So that's the concept. All you need to know is that if you work out the math here, the value of x 0.05 at most on either direction. If you work that out, multiply that by 20, again if you work out the math, then what you get is at most 1 if x is 0, the center, or at most -1 if x is either minus 0.05 or 0.05, which is the absolute value of that is just 0.05 times 20. That should be 1. And so you will get 1 minus 1, 0. And where is x going to be 0.05? We're at the boundaries, at the corners, right? At the boundaries, at the corners, right? At the edges, and then u is going to be 0 there, okay? So with the lambda weighting, you avoid the sharp discontinuity. Sharp discontinuity is a problem in math. It's hard to differentiate, and it's a problem in simulation. It's a problem in simulations as well, okay? So that's a little explanation. So we define the top wall. There you go. Well, we also need the slip condition. No slip condition. No slip. So the no slip condition is again a pointwise. No, wait. It's a pointwise boundary constraint. Pointwise boundary constraint. We pass the nodes, that is a requirement. We pass the rectangle, the geometry, that's just a requirement. And yeah, that's right. Out bar has to be u0 and v0, no slip at the boundaries. The batch size, I mean, it's just 1000 again. Oh, yeah, just remove that. Batch size is 1000, and the criteria is whatever y is less than the height, than 0.05, right? Height divided by 2. In this case, because it's all 0, we forget about any sort of lambda weighting, of course. There you go. Are we done yet? No, obviously not. The important bit is to add these constraints to the domain. Add constraint, top wall, it takes the name top wall, and no slip. Okay? There you go. That's the science and engineering part, you see? And it's easy happening here. Nothing to do about neural networks. This is traditional engineering and science and simulations and partial differential equations. You have the constraints with these couple of commands that are fairly straightforward. Right. Okay, cool. Interior constraints. So the interior constraints, okay? So what are the interior constraints? Well, the interior constraints are all about making sure that, okay, so at a given place, what should be, I'm going to show you this. Okay, the interior constraints. So at a given place within the domain, what should be the value of the continuity equation? What should be the value of the momentum x equation? What should be the value of the momentum y equation? Do we know that value? Well, we do. How? Well, let's say we have this model. It's not very pretty here, but bear with me. We have the continuity equation here, right? Or maybe we can sit here. Yeah. So we have the continuity equation here. So the continuity equation is defined like this value. So we know that at any given x and y, the continuity equation must be equal to 0. So what are the u and v approximations, which we don't know yet, that we need to make that happen? If during the training phase we get a given u or v that is not such a u and v that gives you 0 but gives you something else than 0, that's bad. So what are the values, right? That's what the training phase is going to figure out. All we know is that it gotta be 0, so we define that to be 0 in the constraint. What about the momentum x and y? Momentum y. Well, it's a little bit of a math trick they assume you to know. You move the right hand side of this equation to the left. So you move everything to the same side. And it's the same thing we did above. For a given x and y, what are the approximations of u, v, and p that we need for the whole mathematical model to equal to 0? Okay? But you can say, well, hold on, here we don't have it all on one side. Well, that's why it's useful to check out the Navier Stokes file here. Because if you happen to check out the Navier Stokes file here, you're going to figure out that they moved everything to a given side. It's hard to see here, but so let's see. So they have the pressure with respect differentiated with respect to y here. That's here, and it's a positive here, right? Why is that a positive? And they have the pressure differentiated with respect to y here. So why is that a positive? Well, because they moved it, if I'm not mistaken. They move it to the right, to this side, to the same side. Like if you move this to this side, if you move this to this side, that's going to be a positive. And then they have the new stuff, all the new stuff here, new stuff here, new is here, and that's a negative. Obviously they did it explicitly here, so that's why you have new twice here, new here and new here, but it's a negative. Why? Because they move this to the left hand side, this to the left hand side, and that's equal to momentum x, momentum y, and continuity, which should be 0 in general. Now, there's a nuance here. It's only 0 if there's no external force or source term. If there's external source term, and I think we can learn about that somewhere. Navier Stokes external source term. Like if there's an external source term, like the force of gravity, if you want to simulate that, sometimes you don't. External source on the fluid, then it wouldn't be equal to 0. Like if you move this to this side and this to this other side, then it wouldn't be equal to 0. It would be equal to a force or an external source, whatever. It depends on the equation. The external source is the most general term. So if there's external source, then it's not equal to 0. But if you have to know what that value would be. In our case, we're assuming an external source, so we know it's gotta be 0. So that's why they put equals 0. Momentum x, momentum y equation, that gotta be 0. Right. So as we train the stuff, we're going to be looking for approximations of u and y that make the whole equation 0, right? When we put everything on one side, it gotta be 0, right? Yeah, how come? Well, there's residuals here. Yeah, so this whole thing gotta be 0. And so if it deviates away from 0, that's a loss. So we're going to know that's bad, right? Yeah, that's a loss function. The approximation and what it gotta be. It gotta be 0. If it's not 0, it's a loss. Or the further away it is, or the larger the difference it is from what we know it should be at a given x and y, the larger the loss. I have a video where I talk about the loss function in the NVIDIA Modulus. It's an old video when I was getting into... when I first heard about the NVIDIA Modulus, I made a video about it. And I have a video where I talk about the loss function. I'm going to link it. Okay? I welcome to watch it. Okay, yeah, 1 hour. Let's keep going. Yep, so that's what we have right now. I guess I can code it up. Yeah, so interior, so very quickly, right? Oops. Interior, it's a pointwise interior constraint. Nodes equals nodes, geometry equals rectangle. That's just a requirement. The important part is what the outvar is. So continuity equation gotta be 0. The momentum x mathematical model gotta be 0. Oops. And the momentum y gotta be 0. Okay. The batch size gotta be equal to 4,000, and the lambda weighting gotta be equal to pretty much not this autocompletion. No, it gotta be equal to a symbolic called symbol SGF. Symbol SGF is a... I'm going to explain it in a moment. Oh, there you go. That's so useful. I'm going to explain what the symbol SGF is. It's the same thing. It's the same idea as we had before, but they do it that way here. Domain constraint integer, right? Okay, so that's how moment 2 maths, I have a typo. Okay, so that's how we add the integer constraint. Let's explain what an SDF function is. Like, I am 12. No, that's terrible. I think I have it here. What is an SDF function? A sign distance function is a mathematical function that provides the shortest distance from a point in space to the surface of a shape. Yeah, it's a little confusing. SDF function, sign distance function. Yeah, I understand it to be similar to what we did before, you know. I suppose we want to avoid sharp discontinuities at the boundaries. So as we approach the boundaries, we want to make sure that the value of these equations remains 0. Well, they have an explanation here. Just so you know, you can learn more about it here. So the sign distance function, SDF, recommended practices, spatial loss weighting. This sharp discontinuity can be avoided by specifying the weighting for this boundary such that the weight of the loss varies continuously and is 0 on the boundaries. There you go. You can read more about it here. Let's follow the link. Follow the link. Yeah, this sharp. Well, yeah, it's here. Spatial weighting of losses. You can read more about it here. But you know, if you don't know much about it, you just want the outputs, you just follow the best practices. Just recommend. They are the experts. So we keep going. I have here these links. You're going to be able to access this. And this is the domain we have defined. And this is a picture, I think, of the spatial loss weighting, if I'm not mistaken. Yeah, weighting the sharp discontinuities in the boundary condition. Yeah, that's what it's all about. Okay. So, okay, congratulations. We have defined the problem. That's all it takes. We did it. We defined the problem. We have the domain, we have the constraints. Now we need to solve it. We need to define the solver. Okay? So, solver configuration. Let's do the solver configuration. Just before I continue, I'm going to pause the video for a moment. I don't want to lose my progress, so I'm going to pause the video. I'll be back, and I'm going to save that, then I'm going to continue. Okay, awesome, I'm back. I just saved my progress, the first part of the tutorial. So, the solver configuration. So as I mentioned, I wanted to do everything with as much code as possible. There's a little bit of a limit to that. At some point, they do expect you to define a configuration file. Fortunately, they actually also talk about a notebook workflow in which you can convert the configuration file into a configuration object. In fact, it's just a process of Hydra. Hydra is this. Hydra, what is Hydra? No, Hydra in machine learning. So Hydra is a multi-threaded neural network for model distillation with a shared. No, that's not what it is. No, yeah, getting started with Hydra. Yeah, here, this is what I want. Yeah, Hydra is an open source Python framework that simplifies the development of research and other complex applications. The key feature is the ability to dynamically create hierarchical configuration by composition and override it through configuration files and the command line. The name Hydra comes from its ability to run multiple similar jobs, much like a Hydra with multiple heads. So basically, you have like some sort of configuration that you can keep overriding. So there's the default configuration, there's like more specific configuration, and there's like configuration parameters that you can even define in the command line. So it's just basically a very comfortable way to set configurations. This is because in machine learning, a lot of times you need to run things with a lot of trial and error. You don't know what kind of configuration is going to lead to the best results, so you need to play with it a little bit. So that's why they use Hydra. Anyway, they have this configuration file, and we're going to use this configuration file. In this case, I'm just going to copy this configuration file. And okay, so I'm going to get my configuration file. But I'm going to use some notebook magic. Percentage sign twice, not only once. 2 percentage signs. Guys, file. What's the name I used? Config.yaml. Config.yaml. There you go. Can I move this? Let's move this here. Okay. So yeah. So you can see here our configuration file. You can double click on it and we have our configuration file. How do we load it in a notebook? Well, the way they do it when you're working with files is that you use this sort of like annotation, and you give the path of your folder and the name of your file, and then this is just like magic in a Python file. We can't use it in a Jupyter Notebook. I tried, but then I did a little research because it wasn't working out, and I found how to do it in this notebook workflow part of the documentation they have. The documentation has improved a lot. It's like really good now. So here they tell you how to get the configuration file in a notebook. So you use config path, the folder, and the name of the file. In our case, I didn't put it in a folder. I put it just right here. So the way I'm going to get it up is, well, very quickly you do need these imports here. Modulus im.hydra import to YAML, modulus im.hydra import utils compose, and lastly modulus config. Okay, so then you do configuration objects equals to compose config path. Again, I didn't put it in a folder, so I'm just going to put a dot. They did put it in a folder. I just show you that. Where is that? They put it in a folder. I didn't. It's up to you. I put it just right there. It's easier. So the configuration name is config, and the configuration, yeah, that's the name, and that's how we get it. Let's see what does it give us. Yeah, it gives you the configuration object. Isn't that interesting? But they do other things like configuration network directory. For some reason, it wasn't defined in that configuration. We need to add the network directory. I wonder why I didn't have it here, but based on my notebook, based on their example, I think they added here too. Network directory. So we set the network directory for checkpoints. Okay, cool. But lastly, it's better to print it in YAML format again. So we go back to YAML. The whole point of YAML is that it's readable. So here's our configuration. And in fact, there's more here because there are a lot of defaults. That's the whole point of Hydra. having defaults and overriding the defaults. So that's our configuration. Okay, so yeah, we have our configuration for our solver. So now we create the solver. Create solver from Modulus sim solver import solver. Solver SLV object equals to the solver class. We pass the configuration object and the LDC domain. The LDC domain has our network, our constraints, it has everything. Yeah, because if you remember, to the LDC domain, we added, so we had our nodes with the nodes of the mathematical model, the partial differential equation, and the neural network fully connected architecture, which is going to be the approximation of UV and P in the end of the day. We had the geometry. Then we created the LDC domain. And to the LDC domain, we passed. Oh, it's to the constraints that we pass the nodes and the geometry. So we pass the nodes and the geometry to the constraints, and the nodes have the partial differential equation stuff and the neural network architecture stuff. And we pass that to the constraints, and then the constraints to the domain object, and then the domain object to the solver. So that's why it's very clean. So solver equals solver class with the configuration object and our domain with the constraints and the problem definition. Okay, cool. Yeah. Again, the configuration has a few stuff that we won't be talking about. This is specific to the training and stuff. We can use the defaults. It works out fine. So we define it, and then we run the solver. Okay, we run the solver. Now, very important. Don't forget. First, configure the login to see the steps. Otherwise, you're going to see nothing. It's going to be working, but it's going to take like almost an hour, and you're not going to know how it's doing. So you don't want to configure the login. Now, I'm not going to talk about this little script I came up with a little research and ChatGPT. But I think they do talk about it, though. They do talk about it. Let me show that to you. So in this link, which is all about the Jupyter Notebook workflow, they do talk about the logging, and they tell you to do this, but it didn't work for me. This little thing, like it secured this and it didn't work, so I had to troubleshoot a little bit. I don't remember exactly what was the big issue. I wonder if it was. So I get the logger, I set the level. So they added the handler, the stream handler, and all that stuff, but like I also added the stream handler. I think it was setting the level. It was important to set the level. Perhaps that's the only difference. Anyway, I came up with this function that actually checks out if there are handlers already. It removed them because I tried a few times and I didn't want to keep adding to it. So it just removes all handlers. If you have a lot of handlers, you're going to have duplicated logs, which is another kind of problem. So you want to only have one handler so that you don't have duplicated lines. Then the formatter, this is just a nicety I came up with. ChatGPT suggested it, and I thought it was nice. It gives you the level name and the message in the end. Obviously, the message is what the NVIDIA Modulus gives you, and you can add more stuff to it if you want. Like a different timestamp if you want. Anything else, okay? So we configure the login, we test the login. It's very important that you test the login. If you don't test the login, you risk starting the simulation without logs, and that sucks. It's probably better to stop it if you start it and you don't see logs. Okay, so the deciding part. slv.solve. There you go. 1, 2, 3. Let's go. So there you go. So the logs really start here. This stuff, it's stuff I added myself. But the logs start here. Installed PyTorch, whatever. Step 0, save constraints, results to outputs. Record constraint batch time. Record constraint batch time. Save checkpoints to content outputs. Loss. Attempting CUDA graph building, whatever. So it's going to keep going there, and you can see here the outputs. You have constraints, files. These are for visualization. They recommend a software called ParaView to do it. In a future tutorial, I want to see if I can visualize VTP files with Matplotlib or Python libraries, because that's what I like to do. Software engineer here, I like to use Python too. I like to manipulate the objects myself, read the files myself. So I don't want to install extra software to visualize the stuff. So although they recommend ParaView, I want to see if I can visualize that in the future. But do you really need to visualize the interior and the constraints, the no-slip constraints, the top wall constraints? I don't care about that too much. So let's forget about that. Then there's a file here called events.out.tf events. So TF means TensorFlow. That's a TensorFlow file, and you can visualize that stuff with TensorBoard, and they tell you how to do it with TensorBoard. They don't tell you, I think, how to run TensorBoard in a Jupyter Notebook Colab specifically. There's a way to do that, and we're going to cover that in a future tutorial. Having said that, I don't care about that too much either, because the events of TensorFlow are about the optimization. They tell you stuff about the training process that we don't really care about. We want the output. We want UVMP. That's what we want. Then you have the optimal checkpoints and the float network. I think the one we care about there is the flow network file. Yeah, we care about the flow network file. Okay, so from that file we can load the weights. I didn't find how to do that in the documentation of NVIDIA Modulus. I had to learn myself how to load a PTH file and get the weights set up there, and then load that into the neural network model that we have, which is a fully connected architecture. So the fully connected architecture is kind of like a dumb model. It has nothing in there yet. You can in fact insert inputs X and Y to it and get output U, P, and V, but without the weights, it's just going to output nonsense, nothing useful. But with the weights from this file that we're going to get, the flow network file, with those weights, we can insert that into the architecture, the fully connected architecture object, and then insert inputs and outputs and get the outputs that actually are the approximation that we simulated, the optimal approximation of UVMP. And once we do that, we can get the visualizations. So in our case, that's going to be looking like this. In a moment I'm going to show you. So then we can get the visualizations, right? Which is what they do with more niceties called like the pointwise inferential, which we didn't add because we don't need it if we know how to manipulate the output, you know? And it's not that hard, so we're going to manipulate it ourselves, and we're going to get these graphs without TensorBoard, and we're going to get cooler graphs because we are capable of manipulating the outputs ourselves with our own hands. So that's it. I'm going to post the video. Again, there's more stuff here that they came up with. This is what you will be able to see on TensorBoard, the training, the learning rate, and all of that stuff that I don't care about. In a future tutorial, I'm going to show you how to see it, but in this tutorial, we want this. We want the simulation output, and that's what we're going to get. I'm going to pause the video, and we're going to be back once we have this simulation finished. It's optimizing the loss function. It's going down, as you can see. Yeah, this is a smaller number because it's e to the -4, -0.4. It's going down, which is great. Okay, it gives you the iterations, and I think it takes almost an hour. So, okay, I'm going to pause the video and I'll be back with the most exciting part of the tutorial, finally. Look at that, something happened. My simulation failed. Why did it fail? Well, it told me that I cannot connect to Google Colab's GPUs because of usage limits. I have run the simulation a few times in the past couple of days as I was practicing for this tutorial. And so that's funny. Apparently, if I try to connect, it says cannot connect to GPU backend because of usage limits in Colab. So what do? I'm screwed. Wait, no, not really. I'm not screwed. I'm going to connect without a GPU, and I think that I'm going to still be able to load the model. I'm not going to be able to run the model, but that's okay. I showed you how the output files look. They just look the same all the way down. But I'm going to load files from previous simulations that I had. So I'm just going to install NVIDIA Modulus still, but I'm not going to run any simulation. Okay, so I installed the library again. This time I'm not using a GPU backend. The part we care about is loading the fully connected architecture model. So when it comes to loading a model from a file, what you're really loading in general from a PTH file, you're hoping to load the weights. So you have the weights. So when it comes to neural networks, you have the architecture. That's one thing. The network, it's a graph, takes inputs and outputs. You have the architecture, but you need the weights. You need both to have the whole thing that actually takes inputs and outputs, relevant stuff. Without the weights or with the wrong weights, it's just going to give you nonsense. Okay, so it's because we need the model that we need to load this. We're going to load the architecture. It doesn't have the weights yet, but we're going to load the architecture. So that's all we need. So for example, here, let's see, how do we load the model? So to load the model, we use torch.load, and we load the output files that we have. Let's see. Before we load them, though, I want to show you something. Yeah. So this is a top well point. So we're going to take this. We're going to be here. Okay, so loading the model or whatever. Right, whatever. So before we load the model, though, I want to show you this. What happens if we do this? We get a bunch of nonsense. We didn't get one, right? One. This is 0 because it's e to the minus 0.5, right? We didn't get 1 and 0 for the velocities we should have, right? Here, these are the right values. I have this in my file where I worked things out before. But right now, I just did this and hold on, I didn't get 1 at the top well. Why was that the case? because I haven't loaded the weights. So what do I need to load the weights? So to load the weights, what I need is this command, right? So we need this one. In fact, it's this one. This is the one with the weights. Right. But there's no such file, right? It's such a mess. There's no such file because we didn't run the simulation. So I'm going to get it out from my file system. This one. Yeah. So this is the one I care about. I'm not sure I have the checkpoint file. Hopefully I do. I think it's somewhere here. Oh, you probably shouldn't be able to see my stuff. Ideally. Oh yeah. I found another one that has actually the original name of the flow network. Okay. Yeah. There you go. So we load the files. Let's just remove this one. So we have these files, and I didn't put them in an output folder, so it's just like this. Okay, cool. Oh, I need a damn GPU. There you go. I need the GPU, and I cannot connect to the runtime GPU. That sucks. GPU. Let's see, can I do it like this? We're poor, we don't have GPUs, that sucks. I think we can get away with GPUs. We're already trained the thing. Hopefully we can get away with it. So you don't need to do this map location and stuff if you do have GPUs. Otherwise, well, use it. And so what do we get? We get more weird stuff with the optimal checkpoints. I understand the optimal checkpoints to be that optimal checkpoints. It's not the final thing. So I wonder what happens if we do a step here. The last step. Okay. Oops, keys. Keys. Optimizer state dictionary. Let's see. It has some stuff here. I don't really care about this one, but I want to remember what it has. Yes. Yeah. It has this is about the training and stuff. Optimal checkpoints. If we dive more into it, we're going to find, I suppose, at some point we should find the optimal weights, but for every checkpoint. I think that's my theory. But I don't really care about this one. The one I care about is this one. This file has the weights. Linear weight here, linear bias, linear weight, linear weight, linear weight, linear bias, linear weight. A lot of weights. And I suppose that if I try to see one of those things, I'm going to see numbers. Those are weights. Interesting. And that's what we care about. That's really what we care about. Because the way to load a model is this, okay? So yeah, let's bring this up just very quickly. Okay. Oh, hold on, what happened with my other, did I remove it? It's on my, it's back, yeah. I don't know why I lost it here. Okay, so there we go. So this is the way we load a model. Checkpoint equals torch.load. Not this one. And in this case, the name I have right now is this one. This is the original name. So flow network.0.pth. You may need to do outputs if you just run the simulation. In my case, I loaded it from my file system, so it's flow network.0.pth. Checkpoint.eval. We try that. I even wonder if, so I haven't run this cell, I haven't run it. So right now it's outputting nonsense because I haven't loaded the weights. I just want to actually figure out if we really need this step. I'm wondering if this will work. Oh, yeah, don't forget about the CPU thing. So we need this, okay. All keys matched successful, right? We managed to load the weights to the flownet. I learned how to do this from this question on Stack Overflow. It's similar to this question. There was a state dictionary they talked about here, but I realized that I didn't have a state dictionary in my checkpoint weights, and I was like, hey, what's going on? But then I realized that the keys of this look like the weights. So I tried this out and I realized actually this is what it is. These are the weights. We load the weights there. So that's the story of it. So I think that worked. And I think if we do this, it works. It's close to 1, 99.73. I was hoping it would be 1 because in a previous run from a previous file, it was 1.0041. For some reason, in this case, it's just close to 1. I don't think this has anything to do with it. It even says it doesn't have any attributes at all. Yeah. We don't need this. And you know what? Wait. This is a better name. Let's do this, right? And this is what we get. Yeah, so basically V is 0. U is approximately 1. That's what we need. Okay, so here I have more stuff with tensors that I want to talk about. Because I really think it's important. Again, how to evaluate a PyTorch model. Okay. Yeah, so to evaluate the PyTorch model, just as a reminder, this is the fully connected arc. It doesn't have the weights. You add the weights, and then you have the network, the architecture, and the weights, and then you have something useful that you can see here. Because we loaded the weights, now we get answers. That makes sense. So there are a few things here that I think it's useful to understand. So, for example, how to define tensor inputs. So let's see, you may be confused about why I have this stuff here, but don't be so confused. So if you hover over the flownet, the way I understood how to actually get inputs and outputs is because even though it wasn't so explicitly described in the documentation, when I took a look at this fully connected architecture, they had like this example here. And then I was like, okay, they have this example here. So I copy and pasted it and I put it here, right? So it's architecture equals fully connected architecture, which we did before. And in this case, they have an x of dimension 2 and the output is a y of dimension 2. This is not what we really did. What we did before ourselves was different. It was obviously, let's see, it was a key x of 1 dimension and then a key Y of one dimension, and then we have three keys, U, V, and P. In the example they gave though, it's just a very simple example that is different, and it's a test model. What was interesting about this example is I learned how to define inputs in terms of PyTorch inputs. This is important because if you put an input that is not a tensor, it's not going to work. It gotta be a tensor. So that's what I did. I also fear I didn't really need the evaluate thing for whatever. Like I could just it's interesting because if you run this is what you get. But apparently, I learned you can just do architecture and load the input like this, and you get the exact same answer. You see? That's interesting. This is the advantage of playing with this stuff. You may not be an expert yet, but by playing with the stuff, you learn how it works. So that's why you can kind of like skip a few things here and do it like this. Right? And you get the same answer. That's interesting. So this is the approach we're following, and I learned how to get the inputs and outputs by playing with this. Because by playing with this, then I figured, okay, so what is this actually doing? So it's giving me, like if I do 5 here, it gives me 5 inputs, random integers, but in dimension 2. If I want 1, I just do this. If I want 3, I just do this, right? So this way I figured, okay, and then I did a little research on Google and figured that I think I can do rand, and if I do just rand, it's between 0 and 1. Okay, that's cool. We want something between 0 and 1, but in reality we want something between minus 0.05. Yeah, we don't want something between 0 and 1 for our domain. We want something that is more between 0 and 0.1, right? However, we want it to be between minus 0.05 and 0.05. So we just shift it a little bit. That's one way of getting that. Now we have something that is always more than 0.05 and it's going to be less than or equal to 0.05, right? Oh, yeah. So this is how we're going to get our domain. So our input basically is going to be, I'm going to overwrite this variable. I should know what that means, right? And by doing it this way, I can get inputs between, you know what I want, right? Yeah. Okay. So now we have the kind of input that we want for our problem. Obviously, we don't want all of this stuff. This is not part of our problem, so we can forget about it for a moment. That has nothing to do with our problem. It was just an example of PyTorch a little bit with these architectures. So now that we have something formatted as we need to use NVIDIA Modulus, I have a few more tests here if you want to check it out. It's just a stuff that I put here as I was playing with it. Yeah, a tensor. This is the most literal way to instantiate a tensor. Like you cannot just give an array to the thing; it's not going to work. It gotta be a tensor. So you could give it specific points, which is what we did here for the top wall, right? You remember. But in order to give like a lot of points in the domain, we gotta. Well, that's funny. I'm doing random numbers, right? You don't want them to be random. That's funny. Yeah, the way we need to do it is like this. We need to define the x values and y values we want. We need to get a grid. Then we're going to flatten that grid, and then we're going to instantiate the tensors. Okay? And then we get the input. Oops. I'm sorry about that. This is the way to do it. Yeah. So let's actually go that up. Follow along. Okay. So how to evaluate the PyTorch model? Okay, and let's actually finally how to visualize our results. Okay, I hope you understood how to run stuff with PyTorch tensors and insert the inputs and get the outputs. Oh, well, yeah, just one last thing. I think the real way to complete the previous section is like this. Flownet, get input. Yeah, and you get random stuff, but it's still useless. We want to visualize the results. We just understood how to insert the inputs and outputs, but it's not readable. We need a visualization, in order to read, to understand the simulation output, right? So we define the domain, but now we're talking about the domain of values, right? Linspace. It goes from minus 0.05 to 0.05, 100. I forgot to import numpy. Sorry. It's an import, I forgot. We just import numpy. Its values, okay. It's just an array of its values, 100 its values between 0.05 and 0.05, minus 0.05 and 0.05. That's a lot of its values for that small range. We do it for the y values, same thing. What we really want, though, is a grid. X grid, y grid, mesh grid. Yeah, this is what we want. This gives us a grid of values. But so this gives us so we have grid arrays to create. Okay, so flatten the grid arrays to create inputs for the model. Okay, so you don't want it to be in the format of a grid. You want it to be flat. It's flat equals it's grid flatten. To be honest, it's escaping me why it doesn't count as flat from the beginning, if I'm honest. So let's learn together actually. So it's flat and its values. Why is its flat different than its values? That's such a good question. I'm even questioning the sensefulness of this. I'm even wondering whether I needed at all to do this first. We're going to check that soon. I wonder if we really need to do this. I think stuff is flattened from the beginning. The point here is that the neural network takes stuff in a flat way. It doesn't take stuff in the format of a grid, if you think about it. What's important though is to convert to PyTorch tensors. This part is important. It's tensor, torque, tensor. It's flat. D-type. Yeah, that works out. D-type. What's going on here? D-type, torque. Why do I need them in squeeze? We're going to test if it works. But without that, I need to remember when. Okay. Create input dictionary for the model. Dictionary for the model. By the way, ChatGPT was very useful for this, so this is why I'm having a little trouble remembering why exactly arrive at these conclusions. Obviously, you can ask ChatGPT for a lot of PyTorch questions. We may. It's very useful. So this is how we get our inputs. PyTorch. Okay. And again, questioning why we need to flatten stuff. I feel like stuff is flattened from the beginning, and I'm questioning the squeeze bit. So we're going to do it like this, and then we're going to test if we need those things. And we're going to learn something in the process, okay? The important part is that once you have the tensors, you can pass inputs through the model to get predictions. Okay? So output equals flownet inputs. Yeah, you flat, B flat, P flat, and then we reshape. Let's reshape. Oh, that's interesting. Oh, so that's why. So that's why. Okay, that's cool. Got it. So I think we need the X grid and the Y grid for visualization purposes. That's really the reason. Um, because let's see, for example, the first value is 0. So if we get the output, what did we get in the output? Minus 0.021 was the first one. 0. Okay, so that's our output. What happens if we get rid of? So we got it like this, it's flattened. We don't do the X grid thing. Make it flat, and we just insert the values here. What happens? What do we get? Interesting. Interesting. Let's see if we get the same thing. Apparently we kind of do. Yeah, this is the same thing. I think. Yeah. 2.1 to the minus 3 is 10 to the minus 3 is this one. Yeah, it's the same stuff. That's interesting. I wonder why I printed it like this stuff, but it's the same stuff. It really is the same stuff. Interesting. What about the squeeze? Do we need the squeeze? Interesting. Yeah, the squeeze is important. Why is the squeeze important? Mat 1 and mat 2, the matrix shapes cannot be multiplied. The squeeze. I invite you to remind me in the comments why I need a squeeze here. Yeah. So we're going to do it as I had it with its flat. I think really we can do just the values right away. I'm just going to quickly try to get an answer like for example here. Explain in one sentence why I need squeeze here. Use squeeze here to add an extra dimension to the flattened arrays, converting them from 1D tensors to 2D tensors. Oh, that's interesting. With a single feature, which is necessary for compatibility with many PyTorch models that expect 2D input tensors. Interesting. Interesting. Because interesting. On squeeze. Okay. Anyway. Oops, what happened? Okay, so anyway, we get our output like this. You're going to have access to this. I invite you to share in the comments your thoughts about these comments on squeeze. Okay, so we get the output, and now we want to visualize it. I have this script here. Yeah. So this is matplotlib stuff, which is a little bit out of the scope of this tutorial, but the point is that we have our p grid, u grid, and v grid, right? Oh, not yet. We don't have that. Oops, big oops here. U flat output u, and we detach. This command is necessary, and we make it a numpy array. So we get u flat from the output u, right? The tensor here, but we need to detach the tensor and make it a numpy array. And the same for the other two, and then we reshape the outputs back to the grid shape. Yeah, and we get that from the X grid shape, X grid shape, X grid shape. We already have those shapes. We have these grids, right? Oops. So we run this. We have a U grid, a grid. The grid is useful for visualization. What's a grid? It's not like flattened. It's like the domain. You have rows, right? Like this is the corner of our one side of the rectangle, and this is the corner of another. I guess this could be the other corner, right? So it's a grid. It's not flattened, and that's very useful here for visualizing stuff in Matplotlib. So here's a simple visualization script. It's simple. It's really just this line, I think. The rest is just setting the labels and just repeating that twice. A little bit about the subplots in the layout. So we run this. And finally, we get the visualization. I'm very proud of this because it's a perfect replication of the introductory example. Here. They add this point-wise inferencer, which we didn't even add, because I think the whole point of this is just to do the inference, which is the goal, right? But they need TensorBoard, and they need that added overhead, and they don't even tell you here how to get the manipulate the output, which as a software engineer myself, I care about. Because what happens when you can manipulate the output? Well, you can do cool stuff. So, for example, like here I have the exact same script. The X values, that's grid, that's flat, that's tensor, the inputs, the outputs, U flat, V flat, U grid, V grid. I don't care about the pressure here, so I took that out. The only reason I, had the same script again is because, okay, so now I want to add a vector field. So if I do it like this, it's a lot of arrows. So what I kind of need to do is to do the exact same thing, but not with 100 points, I guess. I don't sample 100 points, I sample 20 points. So once I sample 20 points, I can get the vector field like this, looking really nice. And my favorite visualization of all, in this case, I just reuse the sample of 20. And I get a vector field that has color coding in it of the magnitude of the vector. Beautiful. You can see in the top, it's close to, it's 1 basically, right? You can see much here, but it's supposed to be yellow here, like at the very top. Here it's a little less than 1, but at the very top it's yellow. Yeah, I wonder if I can make them here thicker. Scale time, scale 100. Oops, no. Well, at least you can see the yellow here. That's funny. Yeah. Can I make them thicker? Angles, skew, thicker. Yeah. Well, you can always look up how to make them thicker or remove that black line there to see the yellow arrows better. But there you go. Last visualization, we can do streamlines. Again, we can manipulate the inputs and outputs. We have the model. We can get the function to tell us stuff, and we can do a lot of fancy stuff here. This one is perfect, I think. We can see more of the almost color yellow at the top, right? It's kind of like lemon green. And that's it. So we have the streamlines, we have the vector field, we learned how to insert inputs and get the outputs. We replicated successfully the example here. We did it in a Jupyter Notebook. We instantiated the architecture explicitly, not with the configuration file, which I think it's cool. If you're a software engineer, you want to do things, manipulate the objects more explicitly. We didn't use TensorBoard to analyze graphs about like the learning rate or the optimizer, the training stuff. I'm going to do that in a different tutorial, future tutorial. You can always read here and compare with OpenFOAM data. They told you how to do that with the validator. So what we skipped was the validator part. You need an additional file. Read the documentation about how to get this file because it's not in the repo, I think. But if you add this file and you run this simulation, which I actually teach how to run this simulation with files from this repo. I'm not sure if this file in particular, but with files from the repo, I show that how to do that on Google Colab in a different tutorial. But in the future, we're going to do it again with this file in particular. They also add the inferencer stuff, which we also skipped. But nevertheless, we managed to get what they showed here from the inferencer. We managed to get what they showed here from the inferencer because we understood how to get the weights out of the file, an output file, how to load those weights into the neural network architecture, in this case a fully connected architecture, and we understood that we can insert inputs formatted in the way PyTorch expects inputs, and then we get outputs and we handle them in the way we must handle outputs from PyTorch. I know I hesitated a little bit right now about a few steps with PyTorch. That's because I'm not a PyTorch expert, but that's the point. I was like, okay, how do I get inputs into PyTorch? I looked it up and I understood it and I added it. How do I handle outputs of PyTorch? I understood that and I added it. How do I visualize this stuff that I have here? I asked ChatGPT and it helped me. You know, those are small things. You have to have the high-level concept about how the library works, and I hope these scripts help you get to that point faster. And after that, it's just a little software engineering here or there, a little scripting here or there to manipulate the outputs, and you'll get the answers you need. Now, finally, the leaf-driven cavity flow problem is a classic example, but it's very boring. It's one of the most boring examples ever. And so For a future tutorial, I would like to have a more exciting problem, a more exciting partial differential equation that gives us exciting answers. I was thinking about rocket simulations because that's just cool. I want to learn about that. So, but if you have ideas, please get in touch. If you have ideas and want to get in touch with me, also get in touch. I'm looking to see how I can help people in the industry as a consultant as well. So I can help out with that. If you have exciting applications, let me know. Also, it's a dream of mine that this eventually can be a company. I would like to have a company in the space of scientific computing, AI, and simulations, and cloud computing, and good infrastructure for this kind of stuff. I'm a software engineer by background with an educational background in scientific computing, so that's what I have as a dream. So let me know also ideas about future tutorials. Let me know in the comments. Yeah, share your thoughts. Thank you.